I hope you enjoyed the intro video we just had. This is the actual apparatus we used for this lab. This here is a bunch of pipes that Mr. Furter bought from Home Depot. Because of its irregular shape, it's not a sphere or a cylinder, obviously. It doesn't have a set K value for its moment of inertia. And the goal of our lab was to calculate the moment of inertia for this. So, what we had here, the independent variable for our lab was the weight that we had on the string here. We used about 5 different weights, varying from 1 kilogram to 0.2 kilograms. And the dependent variable was time.
Data gremlin.
Okay, so the goal of our lab, as we've said, is to find I. Start and write this up here. Make it big. Find I. So we're going to start off with what we know. What we knew going into this we knew the height that the weight had to fall. We knew the mass of the weight on the end of the string. We knew the radius of the pipe that the string was wrapped around. And we measured, actually in the lab, we measured the time that it took for the weight to fall from the height and hit the floor. So we knew time. And I'll repeat it one more time. We're trying to find I. So we're going to start off with normal torque equals moment of inertia times angular acceleration. And I'm going to rearrange this to solve for I. So you put torque over angular acceleration is going to equal I. We're going to have to solve for torque now. New line. Our torque is going to equal the radius of the pipe that the string was wrapped around, multiplied by the tension in the string that was pulling and causing it to turn, multiplied by tension. So we know the radius, but we still have 2 variables we don't know here. We're missing the tension. So another arrow here. Our tension, it's going to be the mass times gravity, which is the weight, minus the mass times its acceleration, because it is accelerating downward. The tension of the string is not exactly mg, it is minus ma, which is how fast it was accelerating downwards. That's what tension equals. We know the mass, we know what gravity is, obviously, but we're still missing a. So one more arrow here, a lot of arrows. Acceleration we can calculate because we knew the time, we measured the time. Acceleration is going to equal h over t squared. That is derived from a number of basic dynamics equations. And what you have to do now is you have to throw all these variables into everything. We've solved for all the variables we don't know and into terms of things we do. So I'm going to write a final equation here. It's going to be, oh, and I almost forgot here, angular acceleration we haven't solved for. Angular acceleration goes to acceleration divided by radius. And if you throw all these together into one massive kind of I equals equation, you get this. Actually, I'm going to grab my paper for this because it's a big one. I equals your angular acceleration, which would be over r shifts to a. We'll make this r squared here. Get out of there. So this is your equation for what I equals. In terms of the variables we know, now you can calculate I values theoretically, and there obviously is going to be errors, but if you were to assume that every measurement you made was completely accurate, you're disregarding friction and the number of factors, this is theoretically what your I would equal. This is the data you just saw on the table, but graphed. We have torque in the y-axis and angular acceleration in the x-axis. And the slope of this graph, we did a line of best fit here. The slope of this is the I, which is what we were trying to solve for in the first place. So we're gonna, take the slope of this secant line quickly here. We're gonna do rise over run. We're gonna go call that 11 minus 1.5 all over run, which is 7.0 times 10 to the negative 3 and minus 0 because it has an intercept. So we're going to calculate that quickly. Well, that's 9.5 on the top there. And the good old scientific calculator here. 5.0 E3 negative equals our I value, what I equals here. And calculate that, we get probably to the wrong amount of significant figures, but 1,357 is your I value. Moment of inertia.
Yeah, physics.
Okay, we're going to go through a couple possible sources of error now. So just looking at the graph we drew here, which is torque over angular acceleration, obviously, we had to use a line of best fit here. There's some points that are just nowhere near it. It's not a straight line when it should be. A couple of sources of error here. I'm going to go over to the apparatus now. The four things we knew, the four things we measured. Start with the radius here. Where the string is actually pulling here. The radius is kind of wonky here. It's not exactly still. That could have been a definite source of error. Another source of error could have been in the timing. It wasn't our group actually that was doing the timing. I think Maggie did the timing, but yeah, there could have been discrepancy in the timekeeping. Definitely, that would have thrown the results off. There could have been a bit of discrepancy in measuring the height and actually using the ruler here and measuring how high the 70 centimeters was from the weights, and probably the least likely actually, but I don't know, there's probably errors in the weights we used, but least of all, that would be like very small errors. Anyways.